All right, so in this lesson, we're going to be talking about the power rule. So up until this point, anytime that we've wanted to find a derivative, we've had to use the nasty limit definition of the derivative to find a derivative, to find the slope formula for a given function. So, I mean, you remember this thing. It's the nasty limit as h approaches 0 of f of x plus h minus f of x all over h. We've had to use that to find derivatives. So this was the derivative of f of x, otherwise known as f prime of x. We would like to come up with a rule, hopefully, that's really easy to use so we can circumvent this nasty use of this limit definition formula. That is, we want to see if we can find a nice and easy formula for deriving stuff of this form, this x to the n power, where n is basically any number you can think of. So, for example, we want to be able to derive like x squared, x cubed, x to the 3.14, 5x to the fourth, etc. So let's see if we can develop a rule or conjecture a formula using the limit definition of the derivative and see if we can find a shortcut just based on pattern analysis. So for starters, let's begin with f of x is equal to just x. So f of x is equal to x. What type of graph is that? It's a line with slope 1. Derivatives are going to have, they're going to represent the slope of a particular function. So f prime in this case is equal to 1. Okay? And then if we were to use the limit definition of the derivative to indeed prove that this is the case, we'll do the following. Limit as h approaches 0, f of x plus h. So yes, we're going through this nastiness for now, but it'll pay off, I promise. So we have f of x plus h minus f of x all over h, and we need to substitute in our information here. So we have this x plus h. Every place you see in x in your f of x, you replace it with that x plus h. So you have x plus h right here. And then you subtract off the original function, meaning just x in this case. Then you put it all over h, and then you take the limit as h approaches 0. Trying to squeeze it in there. Okay. So can I just plug in my h at this point? No, because you're going to have a 0 in the denominator, and you cannot divide by 0. So we need to algebraically massage this to get that h out of the denominator. So how do we do that? Well, first thing we're going to notice is that these parentheses don't matter. And also, we can cancel out this x with this x because it was plus x and minus x. So this all goes away. This leaves us with limit as h approaches 0 of h over h. But h over h is equal to 1, so you have the limit as h approaches 0 of 1. The limit of a constant is always just that constant by limit laws, leaving you with just 1. So that confirms exactly what we got just thinking about the graph of the function x. All right? So there's that. One thing I do want you to notice here is that f of x is equal to x is the same thing as x to the first power. Okay, because remember, we're trying to find a general formula for stuff of the form x to the n power, where n is just some number, right? Let's try another one. Let's do x squared. We have f of x is equal to x squared. The derivative of that is not as easy to tell because x squared is a parabola. So it doesn't have a constant slope like lines do. The slope changes. Okay? So we need to use our limit definition of our derivative to do this. So we have limit as h approaches 0 of f of x plus h. I like to rewrite this formula just to remind me of what I'm plugging in. Okay, so now every place I see an x in my original function, I'm going to replace it with this x plus h. So I have x plus h quantity squared. Then I subtract away the original function, which was just x squared. Put this all over h, and then take the limit as h goes to 0. Okay? Just like the last example, I cannot plug in 0 because I'll have 0 in the denominator. That causes problems. That's not defined. So what we do need to do here is we are going to need to algebraically simplify this. How do we do it? Foil the living daylights out of that. I'm going to save you some work and save you some time to just do it myself. And you can take this on faith that this is correct. This foiling is correct. So we have x squared plus 2xh plus h squared. So that's just the foiled out version. Then we subtract off the x squared because of this. And then this entire thing is going to be over h. Still can't plug in h yet because we still have the h in the denominator. So we need to cancel out as much as we possibly can. How do we do it? Well, we have x squared. That kills off the negative x squared. All right, so we got to cancel that loveliness. And now let's see what we get. We have limit as h approaches 0 from both sides. We have 2xh plus h squared all over h. Okay, still have the h in the bottom, that's still a problem, but maybe we can cancel it out with some of the h's on top. So notice that in both terms, this one and this one, we have an h in common. So I'm going to factor out an h. Doing that, I have limit as h approaches 0, because you always have to rewrite that. Then you have h times the quantity x squared plus h all over h. So to confirm that this is indeed correct, if you were to FOIL that back through, you would get exactly this top here. All right, and then you can cancel your h's now because they're both being multiplied on top and bottom. This finally leaves you with the limit as h approaches 0 of 2x plus h, but since we don't have an h in the denominator anymore, we can plug in our 0, giving us just 2x. So the derivative of x squared is 2x. So let me write this up top here. So derivative of x, of f of x is equal to 2x. All right, so let me circle this. We have this lovely thing. In the first case, we have the derivative of x to the first is just 1, which, by the way, technically is x to the 0th, like 1 times x to the 0th, because x to the 0 is just 1. All right, so I'll just leave that there for now. All right, so I'm going to add another page real quick, or several pages, because I'll probably need the space. So we just derived x to the first and x to the second. Let's derive x to the third. I'll run through this calculation a little bit faster. My point is not to just do differentiation practice. The point is to see a pattern. So we have f of x is equal to x cubed. We want to figure out what f prime of x is. So we need the limit definition formula. So we have limit as h approaches 0 of f of x plus h minus f of x all over h. All right. Plug in relevant information. This x plus h needs to get plugged in here for x. So that way we have x plus h quantity cubed minus the original function, x cubed, all over h. And then you take the limit. Can't forget that limit. All right. Can't plug in 0 because we have the h in the denominator. So what we're going to do is FOIL the thing in green. Please take my word for it. Again, it's not just this is not algebra practice. I just wanted to go through this to show you where this formula comes from. So FOILing this out, I'll copy paste my limit thingy. Then I have x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Okay, let's see if we can cancel some stuff on the numerator. Turns out we can. We have this x cubed and this minus x cubed that kill each other. And now that we've killed that off, let's skip a step. Look at this top. Is there anything I can factor out of this? Because my goal is to kill this h in the denominator. Can I factor an h out of these three terms? Turns out I can, because I have an h in common across all of them. So I'm going to factor out an h. So I have limit as h approaches 0 Then we have h times 3x squared plus 3xh plus h squared, because I factored out the h. And then I have this h in the denominator. So now we can cancel these h's because they're being multiplied top and bottom. And this finally leaves us with limit as h approaches 0 of 3x squared plus 3xh plus h squared. And since we don't have the h in the denominator anymore, we can plug in our h is equal to 0 at last. So every place you see an h, you're going to replace it with a 0. So you get 3x squared plus 3x times 0 plus 0 squared. But this is all equal to 3x squared. Okay, so 3x squared is the derivative of our original function, this thing. Okay, so let me write that down. And then we have 3x squared as a derivative. I'll box this. Okay. Now, I'm not going to go through the process of f of x is equal to x to the fourth. I'm just going to spoil that one for you because it's just a lot more foiling. The process is exactly the same as the last three problems. So this gives us f prime of x is equal to 4x to the third power. And that is the derivative of that. It works exactly the same way, same foiling, same cancellation. You can confirm that to yourself. Okay, so now let's see if we can write down a summary of the things that we have in purple boxes here. Our goal, again, at the very beginning of this, was to see if we can find a pattern for how we derive functions of the form x to the n, or x to the some number power. And we tried this for several different n values. We tried it for 1 here at top, we tried it for 2, we tried it for 3, and we did it for 4. So let's write down a nice little table of values here. So we have f of x here, and then we have the corresponding f prime of x here. Let's just write down what we found. So the derivative of x to the first was 1 times x to the 0th, which is just equal to 1. All right. X squared we found was 2x to the first. All right. X cubed is the same thing. Derives to be 3x squared. X to the fourth is 4x to the third. And then if we wanted to do x to the fifth as well, that would actually come out to be 5x to the fourth if you used your limit definition of the derivative. So you're probably seeing a pattern at this point. So if I were to do x to the sixth, what would you venture? Answer this to yourself. What would you venture is your derivative? You'd probably say it's 6x to the fifth. And you would be absolutely right to say that. Now, how about x to the 30th? What would you say? You'd say probably, hopefully, 30x to the 29th. So how are we getting this? What is the rule for when we have a power on x? Turns out the rule is as follows. If you have x to the n, where n is your exponent, what you're going to do is take your exponent, bring it down in front, and subtract 1 from the exponent. So what this gives you is n x to the n minus 1. And that's exactly what happens in the left and the right-hand columns here. So to derive, say, x squared, we took this 2, we brought it down in front, subtracted 1 from the exponent, and that's what we got right here. You take the 3, you bring it down, subtract 1 from the exponent, and that's exactly what we got here. Same thing all the way down both columns. So that's the general formula. So no matter what your n is, this is exactly how you find the derivative. You're going to take your x to the n power, and then the derivative is going to be n times x to the n minus 1, just using that approach. So written out, exactly what this is saying here, move the exponent to the front. And I'll also add this little disclaimer, multiplying by whatever's there. Then subtract 1 from the exponent. And that is how you find the derivative of basically anything of this sort of form here. So never again for these sorts of functions, powers of x, do you need to go through the nasty rigmarole of this limit definition of the derivative, because we just found a nice convenient formula for finding derivatives. So this is the power rule. Okay? And this works no matter what your n is. Okay? So let's do some examples of just using the power rule. So let's let our function be f of x is equal to, let's go with x to the 300th power. The derivative is found simply by taking your exponent, you move it down in front, and then subtract 1 from the exponent. Very, very simple. So it's 300 x to the 299th. Ta-da! No limit definition, no h's, no lots of points missing from an assignment, because power rule is very easy. It's our friend. Very helpful. So let's look at another example. Let's use a decimal this time. So if I had x to the 2.1 power, what's the derivative? Same exact principle, believe it or not. No matter what is ugly, no matter what ugliness is in your exponent, as long as it's a number, you can take this, bring it down in front. So you have 2.1 out in front, x to the subtract 1 from the exponent. So this gives you 1.1 in the exponent. Okay, and that's your final answer. No h's, no nothing ugly, just magic. Okay. So yeah, I'm not going to prove the power rule that we have above, because the generalized power rule is kind of tricky and beyond the scope of what we're trying to achieve right now. Let's do another example to illustrate some important property that goes along with the thing I have in parentheses right here, multiplying by whatever's in front already. So let's do 3x to the 50th. What's the derivative of that? Cool thing about derivatives is kind of what we discussed before using the limit definition, is that constants in front can be ignored. So they just come along for the ride. You just worry about your x stuff. What do I mean by that? So here what we're going to do is we're going to leave that 3 there, and then we're going to take our 50, move it down in front, subtract 1 from the exponent as we did before. But now we're going to multiply that 50 by whatever's already there. So in this case, we're just multiplying it by 3. So we have 50 times 3, x to the 49th power. 49th. There we go. So 3 times 50 is 150. Then we have x to the 49th. That's the derivative. So you take your exponent, you multiply it by whatever's in front, subtract 1 from the exponent, and you're done. That's how this works every single time. Let's do another example of that real fast, and then we'll talk about the linearity of the derivative. Okay, so let's go with 4.1 x to the, let's go with, let me change this. Let me go for 4 and then 1/2. Again, this works exactly the same way no matter what number is up there. So just because it's a half, the rule does not change. Do not make up new rules. Use what you know. So we have this 1/2, bring it down in front, multiply it by that 4, then subtract 1 from the exponent. So you have 4 times 1/2 x to the minus 1/2. So you got to be very careful when you're subtracting 1 from your exponents. So 1/2 minus 1 is definitely minus 1/2. So 4 times 1/2, well, that's the same thing as 4 over 1 times 1 over 2. So that's 4 over 2 using exponent rule, fraction rules, geez. X to the minus 1/2. Simplifying that, that's just 2 x to the minus 1/2. Okay, so that's the final answer to that. Pretty straightforward. Take your exponent, multiply by whatever's in front, subtract 1 from your exponent, done. This is the easiest math rule you'll ever learn, and once you do like 5 of these, you'll never forget it, because it's just that easy. Okay, now we're going to talk about the linearity of the derivative. So if I were given a function, so linearity of the derivative. So if I'm given a function of the form, say, f of x plus or minus g of x, and my goal was to find the derivative of this thing. I'm going to give you the general form, then I'll give you an example. It turns out, as we've discussed before, that it's going to just be the sum or difference of the derivatives. So the meaning, you derive them individually. So as a more tangible example in this, if I had, say, x squared plus x cubed, and I want to find the derivative of this thing. So if I let this be f of x, actually, no, let me just go with this. Come on. So I have this entire thing, and I want to find the derivative. So what I'm going to do is I'm going to derive each of them individually and then add them up. Okay, so that's what I mean by linearity of the derivative. It's a linear operator, as we say in advanced mathematics. So I'm going to derive the first one. That gives me 2x, because I take my 2, bring it down in front, subtract 1. And then I add on the derivative of my x cubed. So I have my 3. You bring that down in front, and then you subtract 1 from the exponent. So that gives you 3x squared. So all I did was derive them individually and then add them up. This would work the same way if I had subtraction here. So if instead of having a plus, I had a minus, it would work the same way. So no matter how many functions you're either adding or subtracting together, you can just take the derivative of each individual term separately. So to go along with what I'm saying here, if I had like x plus x squared minus x cubed plus x to the 4th minus x to the 5th. And this is my function, f of x. To derive this, you're literally going to derive this one term at a time and then add or subtract them together based on the sign that you see. So derive the first one. The derivative of x, by the way, since this is technically x to the 1st power, you bring your 1 down in front. So you have a 1 times x, subtract 1 from the exponent, gives you 0. So what is x to the 0th, by the way? Hopefully you answered 1, because anything to the 0th power except for 0 is 1. So I don't even need to write that. I'll just write 1. So then we have then we're going to take the derivative of this x squared. So you take your 2, you bring it down in front, subtract 1 from the exponent. So you have 2x, because this would be x to the 1st, but we don't need to write that 1. Then we have minus x cubed. So you're going to take your 3, you bring it down in front, so you have minus 3x squared. Same thing with this 4. I'm just going through all of these one at a time, deriving them separately, and then just adding or subtracting them together. That's how these all work. It's really, really easy. So you take your 4, bring it down in front, subtract 1. So you have plus 4. Hopefully you can actually read that. It's pretty bright. 4x to the 3rd. And then the final one, take your 5, bring it down in front. So you have minus 5x to the 4th. Okay? And that's the derivative of this nasty sum that we just found. All right? So remember, the derivative is a linear operator. Complex way of saying derive each thing one at a time. Okay? So that's how these all work out. Try some of the examples that you see below in the topics section. Try as many of those examples. See if you can get them before you click on like any means of getting help, before you click on the videos or the solutions. My guess is that you could probably do them just after watching this video. So take up my challenge. Give them a shot.